Yo, what's up guys, Baby Bear 4812 coming at you one more time. Got a good problem today recommended to me by a good friend of mine, and he suggested I do group anagrams, which is problem 49. Amazon has been on it recently more than anyone, Apple and Goldman as well. Nevertheless, it's a good problem, like I said, been around a while. And in this problem, we are given an array of strings, and we need to group the anagrams together. So the instructions are really simple. We can return the answer in any order. And so if our input was eat, tea, tan, ate, nat, and bat, we want to group the anagrams together. So again, anagrams being words that are, they're kind of formed by, if you rearrange the letters in two words and you can get one word from the other, then they're anagrams. I think they give a bit more of a formal definition here. But essentially, you can see here the reason they've outputted this output is, maybe I'll go from right to left. Ate, eat, and tea are all anagrams of each other, so they get their own list. Tan and nat are anagrams, and then bat is only an anagram of itself. We've got an empty entry here, which will return itself, and then same thing with only this one word. So the instructions are super simple. The solution, not as much, still appropriately tagged as medium in my opinion. There are two general ways to do this. I'll discuss both methods briefly, but I'll only do the implementation for the more efficient of the two. All right, so let's jump over to the sketchpad and have a look at what we're working with. So these are, my pen back. There we go. This is the same input that we were given in that example. It's the one we're going to work with. And before we even jump into how to do the solution, when you approach problems like these, or even problems in general, like I always advocate for this, and I'm really going to keep trying to drill it home. Like, you always want to break the problem down to first principles and fundamental definitions. So let's break things down to their ABCs. Let's pretend we're only given two words. How would we check if either of these words is an anagram of each other? If you can answer the question, like what does it mean for two words to be anagrams of each other algorithmically, so how we would implement that in code, that's like a large majority of the problem. The second part of the problem is then to figure out how to actually get this output together. But I'd argue that part's a bit easier. It'll involve maybe one neat trick to speed things up a bit. But generally speaking, if you can break those two components down, you pretty much solve the problem. And so let's start by saying, okay, if we've got an anagram, so we understand what an anagram is, how do I check if two words, let's say eat and tea, how do I check if these two are anagrams of each other? So anagrams need to have the same letters, the same counts of letters, but they may be rearranged in different orders. So if I was to ask you to implement a simple program where you were to say, let me find if these two are anagrams, there are a few ways to do this. I'd argue actually there are three ways to do this, and I'll kind of walk through them one by one. You can start by going one word at a time and collecting the count of every characters. So count characters. I swear I was like spelling candy. Count characters. I'm going to shorten this to characters. And I'll say we can do this potentially using a dictionary. And if we were to use a dictionary, every key would be a character, every value would be the count. And we can compare two words and kind of give them each their own dictionary and walk through line by line and compare whether or not all the values are accurate or not. Second thing we could do is we could sort. So what if we just sorted the string? So sort string. And if we sorted it, we could actually, it would, essentially this one would look like AET, and this one would look like AET. And then we would ask ourselves, if they're the same word, then they're anagrams of each other. Since we rearrange the letters in a sorted fashion, then, like I said, anagrams. The third way, which we're going to run with, which I think is a bit cleaner than both of these, it's similar to method 1, and it's more efficient than method 2. It'll be to count the characters, but using a bit of a trick, which you may or may not have seen before. So I really like this one the first time I saw it, and it's very useful, very, very useful for counting characters. But we're going to do it using a list or an array. So I'll say using an array. And the way we're going to do this is we're just going to set up an empty array, or an array, it's not empty. It'll have 26 values, each of which will be initiated to 0. So we'll start with 0, 0, and we'll go all the way over, 0, and each one of these is going to represent one character. So this is going to be the count of A's, this is going to be the count of B's, this is going to be the count of Z's, and everything else in between. So let's think about what the difference in all these methods is. With these two are actually, they're pretty similar. It's just that the third one is a bit nicer for implementation and kind of comparison, which we'll see in a minute. This one, typically, if I give you, a word that you want to sort, then the sorting time will be n log n, not long n log n is what it'll take you to sort. If we were to count the characters using an array, it would only be log of n time. It would be linear. We actually just do one walkthrough, and every single character that I see, I'm going to increment its count here in the count array by 1. So counting the characters is definitely going to be faster than sorting each of the strings and then comparing. Now, so asymptotically, this will give us a nicer analysis than while sorting. I will say, I'm just going to give you the heads up right now. If you implement so this problem we can actually implement in a very similar way using both sorting and counting this way. I'm going to implement it with counting because it's asymptotically better. Now, someone correct me in the comment section below if you see an issue with this problem, or with my following statement. But when I ran the code both as a kind of sorted fashion and using the count, the sorted turned out to be a lot faster in terms of the percentile one where you're landing. I believe that's the case, potentially because the words and the inputs that they're giving us are very short. And if they're very short, then it might end up being faster to actually sort them first. But if our words were to be, super large, then again, asymptotically, this would definitely be the way to go. So that's the reason I'm going to implement this method here and not the sorting method. But anyways, before we even get to like the full logic of how we're then going to output the answer here, I wanted to clarify what the different ways were of kind of clearly defining whether or not two strings were anagrams. I will also say that this method here, remember, it will use constant space. It'll use constant space if we're just counting the characters in an array, because in the English language, we're using only, I believe, lowercase English characters here. So at most, we'll take up 26 units of space, O of 26, which we simplify to O of 1. If I then want to compare whether two words are anagrams, I would simply loop over both arrays at the same time and say if the two arrays are equal at every step, then they're anagrams. And what's nice again here is we will only take 26 steps for every comparison. 26 steps, O of 26 is basically O of 1 when we reduce it down to the, again, asymptotic analysis. And so the comparison of these will actually also be O of 1. So with all that said, let's think about how we can actually implement something like this. So can I not? Nope, I can't. All right, take it back. So I'm gonna move this down. And let's imagine the following. If I was to say, I want to group every single word together that is an anagram of itself. So if I see eat, and then I find tea, I need to identify, okay, these two are anagrams, fine. If I compare every single word with every other word to see if they're anagrams, like eat with tea, eat with 10, eat with 8, so on and so forth, and then tea with 10, tea with 8, that would give us n squared time, where n is the number of words. And for every single one of these, we'd have it would take us, I guess, k steps to walk through each word. For these analyses, by the way, I'm going to assume each word is of length k. So maybe I'll say n is the number of words, and then k is the number of characters per word. So c characters per word. K technically can then represent the maximum length of any of these. I'll just assume that they're all of length k. It'll just make the discussion a bit simpler. If I was to do this again, this comparison will take n squared steps, and for each one of these walkthroughs of a word to create this array, it would take us k, right? So we would essentially have a k by n squared algorithm. We can do slightly better, and the way we want to do slightly better is by saying, how do I check every word only once and then determine whether or not a word that I check later on, like when I get to 8, is there a way for me to see, were there any other anagrams of 8 of this word beforehand? The answer is yes, there were. There was eat and there was tea. So let's say that I walk through this and just kind of for sake of argument, eat would look something like this. We'd have one count of A, 0 counts of B, C, D, 1 count of E, bunch of zeros, 1 count of T, so maybe I'll do this for T, or you guys know what I mean, and then 0. Okay, if this is the breakdown, it's kind of the composition of this word eat. How can I save that so that every other word that has the same composition will actually kind of be, I can assemble them all together and maybe keep this as like a key value pair in a dictionary, right? Wouldn't it be nice if I can keep this composition and say match all words with this composition and group them together? And then when I get those, I'll be able to return this. I'll be able to return a list of all of these with the same composition. All of these have the same composition. All of these have the same composition. If I can do that, then I win. The difficulty, though, as some of you may have noticed or may be noticing now, is that if I was to create a dictionary, and this is the case definitely in Python, I believe in other languages as well, I believe, though, I'll move this over, correct me if I'm wrong, this may be allowed in other languages, but in Python, for sure, you can't, if you try to store an array as a key in the key value pair, you are going to get a non-hashable error, so you can't actually hash this. Ideally here, I'd like to have 8, and then I want to have eat, and then I want to have whatever the other one was, t, right? So what do I do here? How do I actually store these then with this composition being the key? One way, which is a pretty clever way to do it, I didn't think of it myself, I wish I had, but you can hash a tuple. So what I can do is I can actually just put this in a tuple, like that. And then every single time an item comes in, I can say if it matches this entry over here, then as a tuple, then append onto this array. The other way you could do it, I guess you could technically create a string out of this as well. So you can 1 0 0 0 1, and then a 1 here, and then a whole bunch of other zeros. You could hash it like this as well. This way is a bit nicer syntactically, just to take the list, stick it in a tuple, and then append these values on. And that's really the approach that we're going to be working with here. And just to give kind of the space and time complexity. So the time is going to be to walk through every single word. We have n words, right? So we have n words, and each word is going to be of length k at most. So it'll be O of n times k, because we have to walk through every single one, and then to actually create this, I'll keep calling it the composition. Then, even if I want to kind of compare the compositions to what else I got in here, then those are constant time comparisons, because I'm only doing a walkthrough of kind of 26 characters. Space complexity will be, let's think about it. So we've got for each one of these words, I want to create its composition, which will be O of 26, and there'll be n of those, excuse me. Hypothetically, we can have n items here as well, right? So we can have n items in the dictionary. So I believe that this also will be, O of n. If I made a mistake, I'll watch this video back and I'll leave a correction in the description below if this isn't correct. I believe the space will be O of n, and again, the space will be taken up by the fact that we'll have n compositions of words that we're going to be creating. And yeah, so that's the logic behind the approach we're going to run with. Again, you could do a very similar implementation with this sorting strategy here. It'll work. I believe this one's more efficient though, so I'm going to go with the counting characters. So with that said, let's begin by doing the following. I'm going to have a result dictionary that I'm going to return, or rather, what's going to happen is this. I'm going to create a dictionary, and I'll have each of these compositions as a key, right? A bunch of these compositions, and then each one of those will have its own list. And I want to return all those lists at the end. Notice each of those lists is the value, right, of the key value pair. So I'm going to have some sort of result here, and eventually I'm going to want to return my result.values, and that will actually return in a list. Oh, my lip's itchy. It'll return in a list all of the values one by one. So I'm going to want to make my result a dictionary. I'm going to use the default dictionary, default dict library here, and each entry is going to have a list as its value here. So for those of you unfamiliar with the default dict, it's just like using a default dictionary, just like using a standard dictionary with curly brackets. If you use a standard dictionary with curly brackets, you then need to ask yourself at every step, is the key that I'm searching for in the dictionary? If it is not, put it in and initialize it. Otherwise, append this value, this word that I got to my list. This allows me to skip that step of having to check whether or not the key is in or not. It just makes the code cleaner and nicer to look at. So I'd recommend you look into it if you're not familiar with it already. Now, we're going to want to look at every single word in strings. So what I'll say is for word in strings, we're going to want to do the following. We're going to want to do one of those character count compositions. So I'll say count is equal to 0 for every character. So 0 for the range of 26, meaning that we're going to input 26 zeros into this count. And then I'm going to look at every single character of this word individually. So I'll say for each character in the word, I'm going to want to append count of some index by 1. And so how am I going to append it? Let's say I've got the letter A. If I want the letter A, I'm going to want to append index 0. If I've got the letter B, I want to append index 1, so on and so forth. So I'm going to take whatever the ASCII code is of my character, and I'm going to subtract from it the ASCII character. Oh my god. I don't know what's wrong with me, I'm sorry. I'm going to subtract from it the ASCII character for lowercase a. That way our indices will match up from 0 to 25 inclusive, so 26 characters in total, to increment through on this count. Once I've actually made this count, I'm going to want to go to my result, and I'm going to want to access the key of that count, okay? And again, this is, right now, we're just kind of declaring it as an array, so we're going to change that. But we're going to take this composition, so imagine this composition looks something like this at this point, and I'm going to want to take the word that I'm at and append it to the list that's related to that composition. So I'm going to want to append the word. Now, we said that if we try to do this, and so actually, you know what? I'll just run it for you guys, and you'll see the error. If I run it for you, it says unhashable type list right over here. So what we could do is, like I said, save it as a tuple instead. If we save it as a tuple, then it'll work just fine. And so I'm going to run that here, and there you go. Again, I know it says that the submission time is super slow. I checked out all the faster ones. They all do the sorting mechanism. The sorting one, I think asymptotically would take longer, so I'm surprised as to why it would get better run times. The only thing I can think of is if all the words are really short, and then kind of with the really small value of k, then the sorting might be quicker. But overall, both approaches are good. Make sure to talk about both of them if you get this question in the interview. And yeah, so just like quick recap, what we did is we said we need to kind of strategically define, not strategically, I fucking hate that word. We need to systematically define is what I meant to say. We need to systematically define how we want to compare to see if two words are anagrams. I gave you 3 different ways of doing it up here, with this one in my opinion, or not even in my opinion, but just kind of factually this one being the most efficient, and my opinion being the cleanest one to work with. Once we did that, we then just needed to decide how are we going to go about walking through these in a clever manner where we can do one walkthrough of every single word. And the way we do that was by noticing that we can store the composition as the key of the key value pair in a dictionary, but we needed to get a bit clever in understanding that we can't hash a list, and so we'd have to store the key as a tuple instead. I hope you guys found that useful. I hope you found it educational. I hope you enjoyed it as always. Don't forget to like, share, comment, subscribe, all that fun stuff, and I'll see you guys in the next video. Peace.